SHA-256, which is the secure hash algorithm 2, producing 256-bit hash values, is specified in the NIST FIPS publication 184. This FIPS publication includes the specification of SHA-1 and all of the SHA-2 family of hash functions, and the main entry point of the specification of SHA-256 is chapter 6.2 on page 21, which specifies that SHA-256 can be used to hash messages of length up to 2 to the power of 64 bits into hash values of length 256 bits. To hash a message, SHA-256 internally goes through two stages, where the first stage is a pre-processing of the message, and the second stage is the actual computation of the hash value based on the pre-processed message from the first stage. This is now the first of two parts demonstrating how to implement SHA-256 in Python straight out from this NIST specification, and as this sounds very exciting, let's just get started with the demonstration. To drive the implementation of SHA-256, I chose the official test vectors as provided by NIST as part of its cryptographic algorithm validation program, from whose website a zip file can be downloaded that is full of text files containing the official test vectors for the various specified hash functions. For this implementation, the first vector I chose is the first test vector contained in the SHA-256 short message text file, and is essentially just the test vector for hashing the empty string whose expected hash value is E3B and so forth when expressed as a hex string. The second test vector I chose is the first test vector contained in the SHA-256 long message file, which is a test vector for a 163-byte message whose expected hash value is 3C5 and so forth when expressed as a hex string. The last test vector chosen to drive the implementation of SHA-256 is a test vector for the string Fundamentals of Cryptographic Hash Functions, where I know from the previous demonstration on how to use cryptographic hash functions with the Python cryptography library that the expected hash value for this string is 41B and so forth when expressed as a hex string. These three test cases I considered enough to drive this implementation, and with having at this point just a dummy function for the SHA-256 implementation, returning an empty string, all the test cases were happily failing as desired. Having the driver ready, I proceeded to sketch out the implementation of SHA-256, where my aim was to write this implementation of SHA-256 with Python in such a way that it is very closely resembling the official specification of SHA-256, which is given as a pseudocode in chapter 6.2 of the NIST specification. The first stage of SHA-256 is a pre-processing stage where an initial hash value is set in variable h, and where h will subsequently be updated multiple times, and at the very end will contain the final hash value computed for the input message. The second step of the pre-processing stage is then to pad and parse the message into blocks of 512 bits, which I at this point delegated to a yet to be implemented function. Following the pre-processing stage is the actual hash computation stage, which subsequently processes all the 512 bit blocks as produced by the pre-processing stage. For each of the 512-bit blocks of the preprocessed input message, a message schedule is created in the array W, where the first 16 32-bit elements are just the 512 bits of the current 512-bit message block, and the following 48 32-bit elements of the array W are the result of various functions that are yet to be implemented. The hash computation stage then reads the current hash values contained in H into a set of 8 working variables and proceeds to what I will refer to as a shuffling step. In the shuffling step, the working variables are repeatedly shuffled and additionally are augmented depending on various yet to be implemented functions and the message schedule created beforehand. Once the shuffling step is finished, the temporary hash value contained in H is updated with the values contained in the 8 working variables. Once all 512 bit blocks of the input message were processed in this manner, the resulting hash value is the concatenation of the values contained in H. Having the SHA-256 implementation sketched out on this very high level, many functions were then left to implement, and the function I proceeded to implement first was the function delivering the initial hash values as specified by chapter 5.3.3. From chapter 5.3.3, it's clear that this is just a set of 8 32-bit words, which I copied into an H0 array and returned a copy of it from this function. Then I proceeded to implement the preprocessing of the message, which is specified in chapter 5, where the first step to the preprocessing of the message is the padding of the message to a multiple of 512 bits, which itself for SHA-256 is specified in chapter 5.1.1. From this chapter 5.1.1, it can be seen that the padding of the input message to a multiple of 512 bits is achieved by appending to the message a 1-bit and a 64-bit tail at the very end, where the value of the 64-bit tail is the length of the input message in bytes. In between the 1-bit and the 64-bit tail, a necessary number of 0 bits are added, such that the overall message with this padding is a multiple of 512 bits. Once the message is padded to a multiple of 512 bits, this padded message needs to be parsed, where this parsing is defined in chapter 5.2.1. This chapter 5.2.1 defines the parsing of the padded message to be the splitting of the padded message into 512 bit blocks, where each of the 512 bit blocks is actually considered to be a block consisting of 16 32-bit words. This is quite straightforward, and to ease the later implementation, I opted to have these 16 32-bit words be represented as 16 integers. This concluded the preprocessing of the input message, which now sees the original input message to be padded to a multiple of 512 bits and sees this message parsed into blocks of 16 32-bit integer words each. Going back to the high-level sketch of the SHA-256 implementation, it was clear that next to implement were the various functions making up the SHA-256 hash computation stage.